tactical robot for Project 2 ENGR141, developed and presented by James Dwyer, Cole Hobbs, Alex Combs, and Blake Richardson.
Game strategies. First priority, if possible, the computer will win with the next move. Second priority, the computer will move to block a move that would otherwise cause it to lose. Third priority, the computer will prevent the opponent from creating a fork. Fourth priority, the computer will move to create its own fork. Lastly, if none of the above are available, the computer moves to a random pattern designated in the code. Normally, some type of fork is being made or able to be made, depending on the computer and defending. How we did it. The AI constantly changes its decision throughout our AI function. The highest priority moves are placed at the bottom of the program in if statements, and the lowest are placed at the top of the program, also in if statements. If the AI can find a better move, then it replaces the output coordinates with the new, more prioritized coordinates.
Example moves. If the player's first move is to the center, the computer will play to a corner. If the player then plays to a corner, the computer will move defensively to prevent a fork by placing it in a corner. The game will then result in a tie if the player moves correctly to block the computer. If the player's first move is to a corner, the computer will move to the center to block all diagonals, what we thought was the smartest strategy. The computer will then create a diagonal, and if possible a fork, that not only blocks the player's last move, but also forces the player's next move to be a blocking action. The computer will continue to make the player block until the game is a tie, or the player makes a mistake and the computer wins.
Why our strategy? Our strategy is very similar to those online. However, we chose the middle space as being a high priority move. Mathematically, the middle space has 4 possible 3-in-a-row opportunities, whereas any other only has 3. And thinking about it, just about every possibility for a fork comes from the middle square. So, if our computer gets the middle square, it will automatically start making a fork if possible. And also, in the process, it will defend multiple forks from the opponent.
Calibration. We use the touch sensor to calibrate the board. After the touch sensor is tripped, we then have to turn the board 45 degrees more to line it up properly. This position is known as home for the board. This method is used each time after the robot scans or makes a move. For example, if the board rotates 60 degrees, it must rotate back negative 60 degrees. The arm is also calibrated by moving it back as far as it will go using the coast function. This position is the starting position and known as home for the arm.
Scanning methods. The robot will fully scan the board after every move. It determines the layout of the board based on the feedback from the sensor and colors assigned by the player before the game starts in a series of menus that allow the player to select a color for the computer's moves and for the player's own moves. The scan is performed by moving the scanner over the first row of the board and rotating the board 45 degrees, pausing and scanning each spot on the outside of the board. Next, the board spins back to the home position. The arm moves forward over the center of the board and scans the final spot.
Marker placement. The robot takes coordinates output by the program to determine where to drop the ball. Based on the coordinates, in a series of if statements, the function determines how far to rotate the board. The function moves the arm forward over the first row of spaces or over the center based on the coordinates given by the program. The function then rotates the motor responsible for holding the ball 360 degrees, allowing the ball to fall onto the board in the correct space. The board then returns to the home position to complete the move.
this one falls on here, this one falls on.
Yeah. We'll keep this one the same.
Crap, I forgot this one.
Alright, so we're starting up our function here. On click start. First part of the program is just to calibrate the board, get the board set for us. And then here it's just asking for our name, and then we're going to say computer versus computer for this video. Play speed's going to be fast. Alright, computer 1's move. Alright. First move. Alright, so now it's saying computer 2's move, so go in here. And back to computer 1's move. The time in between moves is it doesn't have to be this slow, but just for like clarity and just for the fact that I guess to make the moving parts more accurate, we made them a little bit slower. But and over here, the board is updating with every move, so just showing that. And it's blocking itself, so the computer's doing good. Everything's checking out, so we'll just watch it until the end. Thanks. Alright, it's a tie. Thank you for watching.
Citations. The first website you see was used to create the strategy of our tic-tac-toe robot. While all the strategies suggested on the website were not used, they were used as a guideline for our own personal strategies. The second website you see is the lab manual for the robotics for the robot and how to write the program to communicate with the robot through MATLAB.